Hello everyone. So welcome to the third lecture for mechanical behavior of materials part 2. So in the last lecture we discussed about the English criteria, that is stress based approach. Okay. And in the third lecture today we are going to discuss about now Griffith criteria, which is energy based approach for fracture mechanics. Okay. So let's start. So we are going to talk about Griffith. Okay, Griffith criteria. So the equation what we derive for English, remember that is a necessary condition, but that is not a sufficient condition for crack propagation. Overall, the energy should be minimized for any crack to propagate. Okay, and that's when Griffith criteria comes into picture. So the equations were necessary conditions, but not sufficient condition for crack propagation. Okay, so overall energy of the system must reduce and this is what Griffith criteria states. Okay, so now let's understand this concept using the diagram. So we have an infinite plate so again, since I'm drawing these zigzag lines, you should know that this is an infinite plate. And here we have a crack. Okay, and its length is 2a. 2a. Okay. So this is an infinite plate. Second point is that there is a crack which is through thickness crack. Okay, that means you can see, it goes through the thickness. And thickness is say B, and then you are having a stress of sigma. Okay, let me now draw here the stress trajectories, what we have discussed. Let me draw it in the subsequent slide so that it becomes more nice. Okay, so overall, if you see, whenever we have a crack, there are two energies associated with it. The first one is, since there is a crack, you're going to have two surfaces associated with this crack, right? And these two surfaces are going to have surface energy. Okay? So there will be increase in energy due to the creation of these two surfaces. That is point number one. And second, there will be decrease in the strain energy because of the formation of track, and that I had explained during the concept of stress concentration. Now I'll draw the schematic again, and then you will understand what do I mean by decreasing strain energy. Okay, and overall the system, the energy of the system has to reduce if I want this particular track to propagate. Okay, and that is how what the Griffith criteria states. So I have this track. So this track is inside that infinite plate. Okay, so let me just draw now the top one, top surface, and the bottom surface, and this is infinite. Okay? And then I am drawing the stress trajectories. Something like this. And so on. You can have numbers of uh, stress trajectories like this. A line of forces also, right? Same thing. Okay, so there are two energies associated with it, as I mentioned. So two energies are associated with track and its extension. Okay, the first one is increase in the energy. This point is important. It's increasing. Increase in energy due to creation of surfaces. So you are forming the track. So these two surfaces we are talking about. So there will be increase in energy because of the creation of these two surfaces here. Now I'm drawing here. Okay, so there are two surfaces. So this is, since this is increasing the energy of the system, this is in fact restricting the track advance. Okay. Now the second point is decrease in strain energy. Okay, that means elastic strain energy will be released due to formation of track. Okay, or track advance. So now there is a decrease in strain energy because of the formation of track. So since the energy of the system is decreasing, this is going to be the driving force, isn't it? So this is driving force for track tension. Okay, so one is decreasing the energy of the system, and another one is increasing the energy of the system. Okay, and this decrease in strain energy is because of this region. This I had discussed, right? Okay, so this is the region because of which there is a decreasing strain energy of the system. So one is positive, one is negative. Okay, now let's see the calculation quantitative version. So increasing surface energy let's say this is E surface or E surface. Okay. That will be given by, it is related to two surfaces, right? So they are going to have surface energy. So we can write 2 into 2A into B into gamma. Okay. So this 2 factor here is coming because we have two surfaces. Gamma is what? Gamma is surface energy per unit area. Now, if I assume it to be cracked, for all practical purpose, I can assume the two surfaces. So if I mark here two surfaces as 1 and 2, I can assume these two surfaces to be flat, isn't it? So that surface area is going to be the length, okay, which is 2A, and the thickness, which is B. And since gamma is surface energy per unit area, this term here becomes 2A into B into gamma. Okay. So what is gamma? Gamma is surface energy per unit area. So this becomes 4AB gamma. So this is the increase. So this is a positive value, increase in the surface energy because of creation of two surfaces. Okay. Now there will be decrease in strain energy, and that we can write as strain energy released will be given as sigma square by 2E. Okay, you know this. This was discussed in the previous course, part 1. Okay, and this is what? This is given in per unit volume. Okay, so total energy released will be you have to multiply it by the volume of this particular say region here. I have marked in the green shaded, right? Now, if I assume, this whole thing to be circular, so I have this track which has a length of say 2A, right? And if I assume it to be a cylinder, this particular region, right? What will the volume? Volume will be pi A square and B, because A becomes the radius of the circular region, and this is a cylinder. Okay, so pi A square B. But from the diagram here, if you see the schematic on the top left, we can clearly see it is not a cylinder, and the volume is going to be higher than if we assume it to be cylindrical, right? And there are calculations, and based on this calculation, I'm just going to write, it has been figured out that the volume of that particular region can be given as 2 pi A square B. Okay. And how do we remember it? Just remember, that we can assume that the top region and bottom regions are like two different cylinders. And you have to just figure out what is the volume of these two cylinders and add them up. And if you do that, you're going to get 2 pi r A square B. Okay. That is how you can come up with this particular value. It's a trick. Okay. So this is the total energy, strain energy released. And if you solve, this is going to be pi sigma square A square B divided by E. So now we have got two equations. This is equation number 1 and say equation number 2. So one is increasing surface energy, another one is decreasing strain energy because of the creation of the crack. Now these two are competing with each other. Okay, so let's plot these two curves and see what is the total energy plot is going to look like. So total energy we can now write as UT equal to minus E strain. So negative sign I have put here because it is decrease in energy. Now we know that. Plus E surface. Okay. Or we can write UT equal to minus pi sigma square A square B divided by E plus 4A B gamma. And this is equation number 3. So this is my total energy of the system because of the creation of crack under an applied stress of sigma. Okay, this is the Griffith criteria. Okay, so now let's plot it. So the first term, if you see here, so let me mark 1 and 2. Okay, so the first one is what? It's a relationship of parabola, right? Where the axis is A equal to 0. Okay, so what we are going to plot here is energy with respect to A. A is your crack length, parabola, and it's a negative value, and the axis is A equal to 0. So it is going to look something like this. Right? So this is a parabola and axis is A equal to 0. So it is going to be Y axis, right? So this is your E strain. And this is a parabola. Right? Now the second term, which is E surface, it's a straight line. B and gamma is there, and then you have A. So it's a straight line. It is going to be say something like this. So this is your E surface. Straight line. Correct? Now if I combine these two, summation of these two energy. So it is going to look something like now this. Okay. So this is going to be UT, which is E strain plus E surface. Okay. So your total energy of the system is the blue line here. Okay. And what you can see now, that with respect to A, as A increases, UT first increases, it reaches to a maximum value and then it decreases. Okay. And this maximum value corresponds to a crack length which we denote as A star, and it is called critical crack length. Okay. So A star is critical crack length. Okay, so here what is the observation? Observation is UT first increases with A. Okay, it reaches to a maximum at A star and then decreases. Right? That is what you can clearly see. This also means that the crack is going to grow spontaneously as soon as its size becomes A star. And that's why this crack length is called critical crack length. Okay. So we can write crack will grow spontaneously if A is greater than equal to A star. Okay. And A star is what? That's why A star is called critical crack length. Okay. So here what you are seeing, you have an applied stress of sigma. You got a relationship of UT, which is a combination of E strain and E surface. And finally, we have figured out a crack length, which is the critical crack length at which, as soon as it reaches to that particular value, it is going to grow spontaneously. Crack is going to propagate by itself. Okay. So now if I want to calculate the critical condition, right? That is going to be this particular point. I'm showing in the diagram now. Okay, so this is the point where it is critical, right? So if we can, and what is the slope here? The slope of this particular curve, the blue curve, is 0 at that point, right? So if you take the derivative of ut with respect to a and make it as 0, we should be able to find out a relationship which belongs to a critical value, right? After which the crack is going to grow spontaneously. So that is what we are going to do now. Okay. So the critical condition can be obtained by dut by dA equal to 0. So at the maximum point, the slope is 0, right? So let's differentiate and just let me write down here. Ut is minus pi sigma square A square B divided by E plus 4A B gamma. Okay. So let's differentiate this. So we have d by dA and ut is minus pi sigma square A square B divided by E plus 4A B gamma equal to 0. Okay. So this becomes minus pi sigma square comes out, B comes out, E comes out, and D is squared by A, it's 2A. And then here it's 4B gamma equal to 0. Okay. And then will be sigma square will be 2 gamma E by pi. B will just go out. 2 and 4, 1 will cancel out. So it will be 2 factor there. So overall, if you see, sigma will be root over 2 gamma E by pi A. Right? And now I will put it here sigma F because we are talking about the critical condition. Okay. So the track propagating stress or the stress at which track is going to propagate can be given as root square of 2 gamma E by pi A, and this is what Griffith proposed. Okay. So this is track propagating stress. Okay. And one thing you can note, right? There is an inverse relationship between the sigma and track length. So if the track length is higher, sigma F is going to be lower, right? And why it is that? If you remember again, we discussed about the relationship between the track length and stress concentration, isn't it? So if the track length is higher, stress concentration is going to be higher at the track tip. This means that the required stress for fracture is going to be lower, and that is what this criteria is proposing also, isn't it? So it's a very nice relationship between the track length and the fracture stress. And we can correlate this with the stress concentration concept we have already discussed before. Okay. So now what is the variation with respect to stress? So this is for a constant stress of sigma. If you remember the whole concept we discussed, right? So if we increase the sigma, track length is going to be the lower, the critical track length. That makes sense, right? So let's plot it. So variation with respect to stress. Okay. So you are going to have something like this. UT. So now we will have only UT on the y-axis. X-axis is always A here. Okay. So we are going to have three plots. 1, 2, 3. Okay. So this is sigma 1, sigma 2, sigma 3. Okay. And then for sigma 3, we are going to have one critical stress A3 star. For sigma 2, we are going to have A2 star. And for sigma 1, is A1 star. Okay. And here we have sigma 3 greater than sigma 2 greater than sigma 1. Okay. So increasing stress increases the driving force. Okay. Because your track length is now becoming, critical track length is becoming lower and lower. Okay. And also the height, it is also going to decrease as you increase the stress. So if you have more stress, right, there is a more driving force, which is also intuition, right? It says that if you apply more stress, right, it is going to be more effective. Okay. One more relation is there, or observation. So we now know sigma f is root over 2 gamma e by pi a. Yeah, so there is an inverse relationship, something like this. A and sigma f. So if I give you a plate, same concept we discussed with the stress concentration. If I have a plate, same width, okay, same width, W and W, and then I have one small crack here and then one big crack here. You see the relationship, right? So condition 1 and condition 2. In condition 2, you have higher track length. So sigma f is going to be lower based on the Griffith criteria. Okay. And the same concept we discussed during stress concentration, if you remember. If you have higher length, the stress concentration at the crack tip is going to be higher. That means the required stress to fracture is going to be lower, which is given here. Okay. And we can write this as sigma f root pi a equal to 2 gamma e. And this particular left side you are going to see later a lot. Okay, this is related to the stress intensity factor. Okay, and in this case, I would say it's a fracture toughness because we are talking about now sigma f, right? And the right side, this is also equivalent. So this is your fracture toughness. We are going to come to this terminology fracture toughness eventually. Okay. Okay, so we have figured out the stress, fracture stress using two criteria, right? English as well as Griffith. So now let's see which one is valid when and what is the relationship. Okay. So comparison of stress criteria and energy criteria. Okay. So based on the concept given by English, if you go through your notes, we had calculated sigma f and S. I am writing this subscript S here. I am writing because of stress. Okay, so sigma fs we can write E gamma rho by 4a r naught. We have discussed this. Okay, and today we calculated sigma fe where E is energy based. So this is 2 gamma E by pi. Okay. So this one is stress based and this one is energy based. Okay. So in a stress based, we have discussed if rho increases, sigma fs is going to be also higher, right? And in the second one, energy based, if A is higher, sigma Fe is going to be lower. So based on these two formula, you should be able to now know what is the relationship of stress with respect to the crack length and the crack shape. These two, you should be now clear. Now, if I just equate these two, what we are going to get, so let's say compare, we are going to equate, so it is going to be E gamma 4a r naught, and this is square root is gone. Okay, so 2 gamma E by pi A. And if I just calculate, the rho is going to be 8. Gamma gamma cancels out. E is gone. So 8 R naught by pi. A is also gone. And what was A? That was the curvature of the track tip. And R naught is your interatomic distance. Okay. And A is as usual half track length till now. So now if I want to calculate the fracture stress, which one I should use, right? And I have already mentioned that the stress-based approach is a necessary condition. It has to be fulfilled, but it is not a sufficient condition. And that's when Griffith criteria came into picture. So that is the energy-based approach. Okay? And that is a sufficient condition. So in general, the higher value between sigma fs and sigma fe would be the fracture stress. That makes sense, right? Whichever is higher is going to be my fracture stress. So if rho is less than 8 R naught by pi, okay, sigma fe would be greater. So if rho is 8 R naught by pi, both are equal. And if rho is less than 8 R naught by pi, you can calculate it is going to be sigma fe is going to be higher than sigma fs. See, remember one thing here. If you see sigma fs, there is a rho term. So it depends upon the curvature of the track. There is a term also, but there is rho term also, which is very important. But if you see the energy-based approach, there is no rho term. There is only a term. That means it is assuming the track is infinitely sharp. It is very, very sharp and there is no dependence upon the track shape. It is only dependent upon the track length. Okay. And this is very well valid when it is a brittle material. I have already mentioned before that if it is a ductile material, then what is going to happen? Because of the plastic deformation, track tip is going to get blunted. Okay, so there will be curvature. The curvature, the radius of curvature is going to increase. So we cannot use sigma fe in ductile materials where rho is sufficiently high value. Okay, and that is what I am going to write now. So sigma fe will be greater and will be fracture stress. Okay, and this is going to be what, approximately 3 R naught. So rho is in the order of 3 R naught. Okay, and that is the case. We just use the Griffith criteria and say, hey, this is my fracture stress because Griffith sigma fe is higher. In any way, if you see, if rho is less than 8 R naught by pi, sigma fs is automatically satisfied. Okay. So for all practical purpose, track tip radius would be in the order of R naught. Okay. In brittle material, not in ductile material. Okay. Therefore, sigma fe can be used as fracture stress for brittle material. Okay. So for brittle material, rho is in the order of R naught. Okay. And we already know that if rho is less than 8 R naught by pi, which is equivalent to 3 R naught, then sigma fe is going to be the fracture stress. Okay. So, we can safely use this Griffith criteria for brittle material because crack is very, very sharp. It is in the order of R naught. But in the ductile material, there is a blunting of the crack and it is not in the order of R0, it is much higher. So we cannot directly use Griffith criteria because it doesn't have rho at all. Okay. So however, in the tile materials, rho increases due to crack tip blunting. Okay, so sigma Fe can't be used safely. Okay, so then there is a modified Griffith criteria. We'll discuss about that also. So if there is a crack tip blunting, and that too very not high, huh? Crack tip blunting, modified Griffith criteria can be used. Okay, so now let's understand this perspective using some numbers so it will be clear. Now suppose you have a crack with rho of 5 into 10 to the power minus 6 meter. Okay? So you have a crack, say length of A, and the crack tip radius of curvature is 5 into 10 to the power minus 6 meter. That is 5 micron meter. Okay, although it looks very, very small, but automatically if you see, it is much larger. Because we have discussed that in brittle material, the rho is in order of 2 or 3 R0, and R0 is in the order of 10 to the power minus 9, 10 to the power minus 10 meter. Right? So, and so R0 here, let me write, R0 is in the order of 10 to the power minus 9 or 10 to the power minus 10 meter order. Right? Now let's calculate both sigma Fs and sigma Fe. So sigma Fs will be given as root over E gamma rho by 4A R0. So this will be, so rho is what? 5 into 10 to the power minus 6, and A is in the order of 10 to the power minus 10, right? So if you just calculate, you are going to get 100 root over E gamma by 4A, approximate value. Okay. Now sigma Fe, this is root over 2 gamma E by pi A. Okay, or if I just say this is 4 root over E gamma by 4A. So now you can see the difference between sigma Fs and sigma Fe, right? Since there is a crack tip blunting and there is no rho here, so it cannot accommodate the crack tip blunting phenomena. And I already mentioned that this is very well valid for the brittle material, right? So if there is a crack tip blunting, that to a sufficient amount of crack tip blunting, sigma Fs is much higher than sigma Fe. So we cannot safely use Griffith criteria for ductile material. It can be very safely used for brittle material, but not for ductile material. So for now, if I want to calculate for ductile material, we can use the English criteria, which is root over E gamma rho by 4A, because sigma Fs is higher than sigma Fe. Okay, now let me talk quickly about the modified Griffith criteria, which includes some plasticity term, and then close this lecture. Okay. So we have discussed about Griffith criteria that is valid for brittle. Now what happens if we have a little amount of plasticity, not very great amount of plasticity. So if the plasticity is limited, then modified Griffith criteria, okay, can be used. And it was proposed by Orwell. So now we are going to introduce the term of gamma S. And this is given as sigma Fe equal to root over 2 gamma P plus gamma S divided by pi A E. So this gamma S here is what we have been discussing till now, which is a surface energy term. Now gamma P is another term which is related to the plastic deformation at the crack tip. So whenever there is a crack tip blunting, we are going to introduce the gamma P, and that is what modified Griffith criteria is all about. Okay. So here gamma S is previously used. So we have been using this surface energy. So gamma becomes gamma S now. Gamma P is plastic deformation energy. Okay. In general, the gamma P is much higher than gamma S. So we can approximate the above equation as now 2 E gamma S by pi A 1 plus gamma P by gamma S. And gamma P by gamma S is going to be much higher than 1. So this becomes 2 E gamma S by pi A, okay, gamma P by gamma S. And this is modified Griffith, which is proposed by Orwell. Okay. And remember, this is valid when there is a little bit of plasticity at the crack tip. That means your radius is much higher than 8 R0 by pi. If it is on the order of 8 R0 by pi, less than 8 R0 by pi, you can safely use the Griffith criteria we have already discussed. Okay. So overall, what we have done till now, we have introduced the concept of both English criteria as well as Griffith criteria. One is stress based, another one is energy based. Okay, and both are related to the calculation of the fracture stress, and both are showing actually the fracture stress is much lower than the calculated theoretical stress, which is in GPU. Okay, and finally we have compared the Griffith criteria and the English criteria, which one we can use while calculating the fracture stress. Okay, so let me stop here. We'll meet next time. Thank you.